What did you get, Charlie Brown?
I got a rock. I got a rock. Rock. I got a rock. 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 I got a rock. I got a rock. I got a rock. Rock. Rock.
What did you get, Charlie Brown?
I got a rock. I got a rock. Rock. A rock. I got a rock. I got a rock. Got a rock.
What did you What did you get, Charlie Brown?
I got a rock. I got a rock. 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 I got a rock. I got a rock. Got a rock. Got a rock. 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 I got a rock. I got a rock. 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 I got a rock. I got a rock.
All right, so we're going to continue from last time where we left off with structures in C and classes in Java. And I just wanted to draw your attention here that we made this student object, or the student structure, and we left it off with coming up with a birthday. And I wanted to show you this kind of syntactic sugar that if you've got a structure, you can go ahead and use the following syntax to declare and initialize the values of that constructor, or of that structure immediately. For example, remember that we've created this date here with a year, month, and day. And so you can use the curly brackets along with a comma delimited list of all of the elements there. So you don't have to do something like this. You don't have to say date D and then D dot year is equal to, et cetera, et cetera, et cetera. So if you have all of the values that you want to immediately initialize it to, you can use the following syntax. And we've seen this syntax before when we initialized an array. All right, so to continue on this, let's go ahead and continue playing around with this structure. What's another useful thing that you might want to do with this structure? Ultimately, you'll probably want to print it out or something, right? So let's go ahead and design and implement a print function. Right? I'll go ahead and come over here. I'll call it print student. Right? Student. There we go. And what should its return type be, first of all? Is it going to return anything? Nope. All right, we'll go ahead and make it void. Right? Because this is we're about to do what we did over here in Java. Remember in Java, we generated this toString method. So we'll go ahead and do the same thing. Initially here, we're just going to print it out, though. Okay? So now what should we take here? We could take a student structure, S, right? But then I'm passing, is this by passing by a value or is this passing by reference? Careful, is it a pointer? Nope. So it would end up passing a copy of the structure itself. Now that's not that big of a deal because if you go and look at the structure, right, then it's a date, which is 3 numbers, so that's about 12 bytes right there. There's another 8 bytes. Year, that's going to be an integer, so that's another 4 bytes. Another 8 bytes for pointers, another 4 for the integer, right? You add that up in your head, there's probably like 50 bytes there or something like that, right? Certainly less than 100 bytes. So that's not that big of a deal, but if you have much more complicated structures, then that can get kind of big, right? In fact, and maybe inefficient, right? So what I'm going to do is instead of passing the student, I'm going to go ahead and pass a pointer to the student so that I'm only ever passing in a memory address to this function, all right? So let's come back over here to student.c and let's implement this. Well, I'm just going to implement this maybe, what was a student? A first name and a last name, and then a date of birth, a GPA, an NUID. So let's go ahead and just print out, I don't know, the name and the NUID. That's good enough, right? If you wanted to print absolutely everything out, then you can go ahead and do that as your own little exercise there. So printf, the last name, comma, the first name, right? And then in parentheses, we'll put the NUID, %D. Right? And then we'll go ahead and end the line. Excuse me. So S, last name, why did I use the arrow operator here? Do you remember? When I've got a regular old structure, what do I use? The dot operator. If I have a pointer to a structure, I need to dereference it, and then I can use the dot operator, but that would involve parentheses. So the syntactic sugar here that allows me to do that with one step is the arrow operator. The last name, then S, first name, and then finally S, NUID. There we go. All right, and we can print that out. Let me go over here to the demo, and let's go ahead and print out Jane here. Jane, who was born on today, looks like, yeah, today, in 2000. Right? So she should be 21 years old today, right? So let's go ahead and print student, right? And we'll pass in Jane. Now, do I need to pass in Jane with an ampersand there? It already takes a student star, a student pointer, and Jane is a student pointer, so no. Would it be correct to dereference it? That takes the pointer and turns it into a regular old variable. It doesn't take a regular old variable, it takes a pointer. So I pass in the appropriate type here. I'm just going to go ahead and compile everything together all at once. Oops. All right, so over here I need to include the standard input-output library now. Why? Because now I'm using printf. Okay? So bring everything together, run it, and we see Jane Doe here. And was that her NUID? Did I not set it? Oops. The NUID should be 1234, right? Okay. So there's some bug here. Let's find out what it is. %D, that looks okay to me. What about this initialization? That looks okay as well. I'm not seeing it. Why is it 0? Anybody see? Okay then, this gives us an opportunity for more practice. And how do I diagnose this? GDB. I need to recompile it using the G flag, certainly. Maybe even also turn on all the warnings. Maybe I can catch it that way before that. And then all the .c. There we go. S is uninitialized in this function. Ah, okay. I didn't even need to run GDB because I had the wall flag right here. Okay. So let's find out what's going on here in student.c. Right. S. So I declare S. I set its NUID. And then I allocate it. I need to allocate that first. Didn't even need to fire up GDB. So kick that, run it again, and hopefully it will work this time. 1, 2, 3, 4. Here's a trick. NUIDs are how many digits long? 8, right? Anybody have an NUID that begins with a 0? All right, you know somebody who does. All right, so this person, Jane Doe here, begins with 0, 0, 0, 0, or 4 zeros, and then 1, 2, 3, 4. How can we get that formatting out of this? %08D. %8D will mean that it's going to print a minimum of 8 columns. No, normally it's going to print spaces, but you can say 0D to print zeros instead of spaces. And it'll pad it out with zeros right in front of it. Cool. All right, let's go back over here to Java really quick. And remember that encapsulation involves 3 things. The grouping of pieces of data that act on that data into one logical unit. We've got that, right? Here with our student, we've got the NUID, first name, last name, ... all that stuff. We've grouped everything together. We've got the protection of data from the outside world. Remember that we made everything private instead of public, so we're protecting it from the outside world. And we've got now the third one is we want a group functionality that acts on that data inside the class. Okay, so let's do that next. If I've got a student, what's a piece of data that I might want about that student? Their GPA, okay. If I wanted to print just the GPA, if I wanted to sort it or something like that. Let's go over here to the demo and see if I can get Jane's GPA. Jane.GPA. Well, no, I can't do that. Why? Because it's private, right? So how do I get access to it? Let's make a method to do it, right? You want access to her GPA, let's go ahead and make what's called a getter method. So public, because of course we want the outside world to see it. A GPA is a double. So then we'll go ahead and call it get GPA because that's what it's getting, right? Now I need to return this object's GPA. Now, when I do that, I'm not accessing the GPA directly. Instead, I'm asking the object, would you please give me the GPA so that I can compare it to my GPA and see who's a better student or who has the better record, right? So if class GPA is greater than Jane.get GPA, right? Then I'll system.out.println. I don't want to say I'm better, but yay, I guess. Else, boo. Right. There we go. And boo, because she has a better GPA than I do. Right? Now, that's called a getter. Maybe I want to do that with everything else. Maybe I want to do that with the NUID because I want to sort by NUIDs. Or maybe I want to do it by the last name or something like that. So, are you going to sit here and watch me type 50 lines to do this? Nope. There might be a better way. Now, also, what if I do want to set the GPA? I've improved, right? I got a better grade, and now my GPA has actually gone up. Me.GPA. I want to set mine to 3.9 now. Can I do that? No, because it is a private variable. So let's go back over into the class here, and how could I potentially do that? I could have a public void, because it's not going to return anything. If I can get the GPA, what else could I do? Set the GPA. Set GPA to double GPA, the new GPA. This dot GPA is equal to GPA, just like I did in the constructor up here. Right? But now this enables me to do some data validation. What's an invalid GPA? Less than 0, all right? Or GPA is greater than, we're only on a 4.0 system, right? So 4.0, right? Then I can throw an exception. I can do error handling, right? Throw illegal argument exception. And I'll just have a name here, invalid GPA. Right, there we go. Otherwise, I'll go ahead and set it. And of course, I need to import this. Oops, illegal argument exception. Throw new, thank you. I thought my spelling was off. Nope, it's good. All right, so let's come over here to the demo and see how I can use this. Me.set GPA to 3.9. Right? And I don't know if that beats Jane or not there. No, it does not. I'm still lower than Jane. But I can now see that if I try to set it, I'm going to set my own GPA here to 4.5. Right? Then I get that exception. I'm only able to do this by establishing that barrier, right? That encapsulation barrier that I'm protecting the data from the outside world. Fine, you can go ahead and set the GPA, but I'm going to check it first. And if it's an invalid value, I'm going to throw it back at you. In this way, I can do data validation, I can protect data, and I can achieve number 2 of the of encapsulation. Yeah.
How did you get the print invalid GPA after?
That was the message that I threw right there.
Oh, okay.
All right. So, again, are you going to sit here and watch me type? No. What you can do is you can go up to source, excuse me, and you can generate getters and setters, right? And then you can expand these out. Oh, I want the getter of the date, and I want both of them for the last name, and I want the setter for the NUID, or I could do all of them, or none of them, or just the getters, or just the setters, right? And it'll automatically generate all this code for you. Now, in general, you don't like setters, because setters means that you have a mutable object. And immutability is a very good thing because it gives you thread safety automatically. Right? So generally, I do not like setting setters. But you know, getters are perfectly fine. Let's go ahead and generate all of the getters. Select all the getters, generate, and you're done. Now, some languages have this built in, like C# will have get. All you have to do is say get, and it'll automatically endow that class with all the getters that you want. But by auto-generating the code, you get the same effect that you don't have to type anything, but then it becomes explicit, right? And then you have a little bit more control over it. I don't want the getter for the NUID. I want to make that completely private, or whatever. All right, so we've achieved even greater number 2 of the protection of data by controlling everything through getters and setters. Now I'm going to achieve this third one here. What else would you want to compute, say, based on this student right here? We printed him out. There's a way to create students. Let's focus on that date of birth there. So what could I compute that is a function of the date of birth? There? Age. Right? So let me go ahead and come down here and let's compute a public int get age. Right? Now I'm still, it's not really a getter because there's no variable called age. But if I did store the age instead of the date of birth, right? Does that sound, which design sounds better? Storing the date of birth and you can always recompute it, or storing the age and then you have to manually update it every time they hit their birthday? That first design seems a little bit better to me because it has more data. It not only tells you when they were born, but you can always recompute their age based on today's date. What if we stored both, though? Maybe that's the best of both worlds. Private, int, age, in years. What's the problem there? Think about that design, storing both the date of birth and the age at the same time. Well, first of all, it's a little bit of redundancy, right? I can get one from the other. I can't get the other from the one, but a date of birth seems sufficient here. But also, their date of birth is fixed, right? What if I set their date of birth was 2000, so they're 21 years old today, but then what's to stop me from setting the age to 50, right? And now we've got an inconsistency in those data representations. Whereas if we only had one variable, and we can always recompute the other one, right, then we don't need the second one. So let's compute it. For that, I'm going to have to look at my notes. The Java datetime library allows you to define local date times, local times, epochs. You can do periods and durations. And what I want to do is a period here. Period. P is equal to, and then it gives you a bunch of library functions that you don't have to manually. How many days have passed since 1971 or whatever, right? What I'm going to do is I'm going to compute the period between today's date, or the date of birth, and today's date, which would be local date dot, how do I get today's date? Now. And that's it. Now, if I run this tomorrow, of course, it will be tomorrow's date. If I ran this yesterday, it would be yesterday's date. But this will always give me the period between these two dates. And now I'm only interested in the years. I could get the years, the months, and the days, and get an accurate that they are 21 years old, 5 months, and 3 days, right? Something like that. I'm just going to be interested in the years. All right. So return p.getYears. There we go. All right. Now let me go over to the demo here and get my I don't know, what did I set my birthday today? Oh, today. Okay. Well, that was 2 days ago. So let's go ahead and set it to, all right, 1990. And then today. Say today. Suppose today is my birthday. All right. And let's get my age. System.out.println. I am percent or plus. What is it? Me.getAge. Years old. I am certainly not that old. I'm even younger. I swear. No. But I'm not going to give you my real birthday. Right there. I'm 31 years old today, apparently. Right. Now, think about this functionality. This functionality, where does it belong? It belongs exactly where I put it. But let's think about a different design. What if I had done this over here in the demo instead? I want to know my age. So I would have to say me.getDateOfBirth, and then do the local date now. And then, instead of me.getAge, I would have to say p.getYears. There we go. There's an alternative design. Pros, cons of each. What do you think? In the class or outside the class? Which one's better? Outside the class? All right, what's your argument there?
I think since you're calling me, like you're calling that object me, I feel like it should be basically where you defined it.
Okay, where did I define the date of birth then? The date of birth seems to be inside that class, right? So think about what I'm doing here by locating this functionality outside the class. Encapsulation. The student is a box, and they have a date of birth inside. I have to rip open that box, pull out the date of birth, which now has nothing to do with the box. I just have a raw piece of data. And I will compute today, and then the period between them, and then output it. Whereas if I had treated the box with true encapsulation, where everything was located inside the box, including the behavior and the functionality that acts on the data inside that box, all I need to do is ask this magic box, how old are you? And it says 31, right? So, located inside the class, any behavior functionality that acts on that data belongs in the class, right? So that I don't have to worry about those details. Now let's go ahead and back it up here and think about it from another point of view. Right? All right, I've got this student class, and it's got a method called getAge. Do I have to worry about any of the details involved in computing that age? That they have to get, that you have to define this class called period, or not define it, but instantiate a period class, and then compute between now and then call this other function called getYears, and then give me back the years, right? Many steps there. Do I have to worry about it here? Nope. That supports procedural abstraction. All right, and that's another, well, we'll talk about object-oriented programming next semester, but that abstracts away all those details. I don't have to worry about it, right? Just like I don't have to worry about how does the square root function work again? Who cares, right? There's a student, and I can get their age magically, right? They take care of it. And I'm able to call it, and they they know how to do it, they have the data necessary to compute it, and they take care of it. Right? Delegation to that class. And so that completes number 3 of the encapsulation. If you have anything that acts on that data, you probably want to put it in the class so that it stays there. Okay. All right, so to review from, originally from structures, I'll go ahead and bring this over. Right? All right, so when you have a now switch your hats back to C. When you have a regular old structure, you use the dot operator, and again, you access member variables. What did I use over here in Java, by the way? Jane dot get GPA, me dot get age. And do you think that we have an arrow in Java or not? The arrow comes up when we've got a pointer to a structure. Do we have pointers in Java? Nope. So there is no arrow operator in Java. But when you have a pointer to a structure, you do use the arrow operator. And it's going to the next line. There we go. Right. Alternatively, you can create an initialization function. You can create a factory function like we did. And you can create other convenience functions, right? A way to print a structure to the standard output like we did. A way to generate a human-readable version of it, right? Et cetera, et cetera. A function maybe to free up memory that you've allocated for that student structure or whatever. Right? Let's get some more practice now by doing a couple of those. Right? Let's see. All right, let's do an initialization function. What I mean by that is this construct student will create a brand new student for you with all of these with all of these characteristics that you just gave us. What if I already have a student structure and I want you to fill in the blanks? Right? That would look very different. Instead of returning a new structure, I would take a structure by reference or by, it had to be by reference at that point, but I could initialize it instead, init student. Right? Init short for initialize. And I will take a student S, right? And I will take all of these other aspects of it. There we go. And I will set all those aspects for you. Now, this is a little bit different than Java because, in Java, you can actually have multiple constructors, and we'll get to that here in a second. But otherwise, let's go ahead and envision what this would look like instead. Okay? All right. Init student. How would I go about implementing this? The student already exists. Do I need to call malloc to set it up? No. I could do some basic error checking, make sure that it's not null, and then if it's null, just return or something like that. But otherwise, if it already exists, I can set the NUID. I can create a string there for the last name and the first name and copy it over. I can do everything over here that I just did before. Copy, paste, return. Now, does that sound like a good idea? Copy, paste, copy, paste. Right? I have virtually in fact, I have exactly the same code here as I have up here, right? Between this line and this line. So let's rethink this. Can I use one function to call the other function?
Just call init
Init student right here. Right? Replace all of that code with one function call. And of course, it would be NUID, first name, last name, year, GPA, and date of birth. Much simpler.
and the pointer.
Thank you. And the pointer would be S. There we go. All right. Now, am I going to be making changes to student? Yes. So I need it like this. But before we continue, let's rethink about the print student here. Am I going to be making changes to the student in the print function? How can I advertise that fact? Const. Right? Const int star gives you an array that can't be changed. Const student star gives you a structure that can't be changed. Now, I'm going to have to match this over here. There we go. Looking good, right? Minimum amount of code here, but maximum functionality. You have options now. If you want to create a brand new student, well, here's a function to do that. If you already have a student and you just want to initialize its values, here's a function to do that. One calls the other, so we cut down on the amount of code that we have. Not only that, but I'm going to show you another trick here, since I think somebody read the documentation and found it. I'll go ahead and share it here because I shared it in the main class. This is these two lines here are a deep copy, deep string copy, right? You can write your own function. In fact, I think that we gave you that function in this last lab here yesterday. Go ahead and feel free to cut and paste that. Otherwise, you can use a built-in function. It's called strdup. So what do you think dup stands for here? Duplicate. Man, strdup. It's not standard C, by the way. It's an extension. But it's in the string library. And let's read all about it by RTMing. The function returns a pointer to a new string, which is a duplicate of the string. Memory for the new string is obtained through malloc and can be freed with free. In other words, it does all that work for you. Right? So, first name is equal to, and it takes care of the null terminating character for you too. strdup of the first name. Excellent. And same thing with the last name. Last name. And that cuts down on a lot of code. Right? Locks, fewer locks are better. Locks are being lines of code. Right? So if you can, until it gets too small. All right, so you got to make it Goldilocks. Right? I think I've mentioned Goldilocks before. Yes, not too long, not too short, just right. Okay, let's make sure that I didn't introduce any syntax errors here. Good, we're still good. All right. Now I'm also rethinking this print student here. Because what if I wanted to print it to the standard output? Well, that's good enough. But what if you wanted to print it to a file? What if you wanted to print it to a socket and send it over the network somewhere? Right? Is there a more generalized way that I could do this?
You could print it to a string and then
I could print it to a string just like Java does over here, toString. Right? Let's do that. So I'm going to return a character array, and I'll call. I could call it toString, but the problem there is that once you have a one toString method, that's it, right? What are you converting to a string? Now over here in Java, you can have as many toString methods you want because they're in different classes. That student class, that date class, that film class, they all have their own toString functions. And so you only need to call them toStrings. But over here, I don't have that luxury because I don't have these objects. So student toString. Okay. And then, of course, I need a student, and I'm not going to be making changes to it, so student star s. Okay? Now, I'm going to steal this code up here because that's the format that I want there. All right? So printf prints to the standard output. If you wanted to print to a file, of course, you would use fprintf. But I liked your idea of let's print it to a string. Sprintf. Right. Now, I need a string to print it to. So char, I can't use s, so I'll use str. There we go. And here's a trick. I'll go ahead and put in str here, and then return str. Now, there's a problem here, but we'll talk about that in a second. All right? A couple of problems, actually. Let's just assume that this works, student to string. Right? How could I use it in print function in my print function up here now so that I don't have to repeat this? Call it student to string of s. Once I've got the string representation of it, you can go ahead and print it out to the standard output if you want to. You don't need to do any formatting at all. Just print that string. Okay. Now, a couple of problems here. Let me go ahead and recompile this with all the warnings. Does anybody see, before I do that, does anybody see the problem here? Yeah, what?
Once you return it as a God.
Yeah, it's statically declared, right? It is on the program stack in a stack frame. When I return from the function, what happens to that stack frame? Popped, gone forever. And that's what this warning is going to be about. Function returns an address of a local variable. Can't do that. All right. So I'm going to have to call malloc and return that value. When I call malloc, I'm going to have to count up how many characters are in the last name, plus how many characters are in the first name, plus how many 8 for the NUID, plus 1, 2, 3, 4, 5, 6 characters for the formatting. Right? That's a lot of math for me. I don't like adding all that stuff up. You can do that if you want, but there's no problem with creating a temporary local variable and then using it, right? To measure the length so that you only have to create a brand new string. And we just saw a quick way of doing that, right? So I can return string duplication of str. And now my warning goes away. There's still something else here. Right? The problem here is that this is not in the header file. I should just take care of that really quick here. There we go. There. All right. Now, the warning goes away. What happens to this thing? Do I have to clean it up? Do I have to free it before I leave? No, because it's in the stack frame. The stack frame goes away, right? In fact, this might be like a, thank you. This will be a stack smasher, maybe? Yep. Attempt to free a non-heap object string. It's just a warning. If I go to this, aborted, free or corruption. Cool. Usually it says stack smasher because if you free up your stack space, that's like saying, I don't need my program at all anymore. Please go ahead and take all of my memory away from me. Right? And that's not good. Right? It'll be cleaned up for you automatically because it's part of the stack. Right? All right, that leads a question up here, though. Is there a problem with this function now? Well, let's go ahead and compile it and see. Everything works fine. Jane Doe, and there's her NUID again. Right? Let's run it through Valgrind and find out. So there are definitely bytes lost. 78 bytes, in fact, directly lost. And there are 9 bytes indirectly lost. What bytes are lost in this function? You called student to string. You got a dynamically allocated string character array here through the call to strdupe. You printed it out, but then what did you do with it? Nothing. You didn't free it, and so it's lost. It's leaked out. And that's why Valgrind is telling us that there's a leak here. Okay? So let's go ahead and free that up, str. You will see that, I don't know how much, not everything has been cleaned up, but enough has been cleaned up that it'll be way less than, remember it was 78 before? Now it's only 56. Right? There's still something leaked here. But 70, what was it, 74 I said? 76, was it 76? Or whatever it was. That was exactly the size of this, well, of this string right here. Right? So 3, 4, 5, 9, 10, 11, 12, 13, plus 8, 21. 21 bytes. Or some 22 bytes, maybe I miscounted or something. Right? All right, excellent. Right? Now I've got this general student to string. I can convert it to a string. I can print it to a file. I can print it to the standard output like I do up here. I can print it to a socket. I can do whatever I want with it. This is way more general, just as this one, I don't know, depending on your point of view, is this more general or is this more general? Right? I think that this one's more general because it doesn't require you to set up the memory for it. But it uses the more specific down here. Okay? Can we get the same thing over here in Java or something similar? For example, the constructor that I have right now requires me to provide the NUID, the first name and the last name, their year, their GPA, and their date of birth. What if I don't have all that data? What if I have a student, Gomer, and I only have their NUID, because they're a brand new student, 4321, and their first name, and their Gomer, and their last name file. Right, there we go. I can't do that. Why? It wants all the arguments. Look at the function over here. It requires an NUID, first name, last name, all this stuff. All right, well, if I want that function, what should I do? Make that function, exactly. In fact, I'm not even going to do that. I'm just going to let it make it for me. Remember that you can go up to constructors using fields, deselect all. I'm only interested in the NUID, the first name, and the last name. Generate that, and there it is.
Is there just a keyword you can use so that you don't have to?
No, some languages allow you to have keywords like for getters and setters, like C#. You can just put it in a keyword get, and it'll automatically endow that class with a bunch of getters or set and setters likewise. But that's like a sledgehammer instead of precision. It gives everything to all of the fields in a class. All right, but let's do the same trick that I did before. Ignore super. Lots of repeated code, right? Repeated code, repeated code. Maybe I can have one of these functions call the other function. Right? And if you're not interested in the year, the GPA, and the date of birth, well, you could go ahead and just make those into defaults. The year, of course, would be null. GPA could be 0, and the local date of birth could be, or the date of birth could be null as well. So I want to call this function student, pass in NUID, first name, last name, what did we say, null, 0, and null. There we go. But I can't do that. Student dot student. Right? It's not a stat. That would be if this were like static. I can't even do that though. I can't call new student either. Right? So, how did this class refer to itself? This. So if I go this dot NUID, I'm referring to my NUID. What if I went this dot some function? I could do something like that. I could go like down here. I'll show you this dot get age. If I wanted to print out the age as well, right? So this member variable, this member method. What about a an actual constructor? It's just this. Right? I'm calling this object's constructor, and it's able to figure out, oh, you mean this one up here because you gave me these 6 inputs. Right? And so the keyword this is used in 3 contexts: to access variables, to access functions, methods, and then to access constructors. Yeah.
You use this when they're the same name.
Yeah. Well, you're in the class, so you can't. I can't say this and refer to a local date or something like that, because I'm in the class right now. This is always bound to that class or to that instance of the class.
Okay, so by the number of arguments given.
Yeah, by the number of it's able to figure this out. If I said gave it only 5, then it's not able to figure that out because I don't see a constructor with 5 arguments. Right?
So couldn't you just pass those 6 arguments into Gomer?
You could, but then that requires you to explicitly provide defaults: null, 0, and null. Right? That's a lot less convenient than just say, I only have, this is the data I have, this is only the data I care about, here you go. But you could do that and restrict, so it's all a design decision, right? By implementing multiple constructors, I'm making this a little bit more flexible to use, right? If I say, I only want this one constructor, you have to use it exactly how I tell you how to use it, then you're going to be giving me a lot of unnecessary data, a lot of unnecessary lines of code. And when you have unnecessary things in your code, cruft, right, then that introduces additional potential failure points. And you want to limit as many potential failure points as possible. Yeah.
So go back to the class.
Uh-huh.
So what if they have another function that takes the exact same arguments?
Can't happen. So for example, I don't know, 2 get age functions. Where's get age? There we go. There's one get age function. There's another get age function that only ever returns return -1. Can't happen. There's a conflict here. Now I could say get age int foo. Now those 2 are different functions because one takes 0 arguments, another takes 1 argument. But that's kind of useless. Right? I could change the return type, but that's not going to work either. Right? Because the compiler can't say, did you mean to call this one or did you mean to call that one? Well, that one returns an integer and that one returns a double. You don't have to store the result at all. Right? So I can't tell which one you meant to call there. I give up. Right? There is one limited instance in which you can do something like that. It's called covariant return types, but we're not going to get into that at all. Right?
And so, if it's a different name, but it takes the exact same parameters.
Oh yeah, you could do that. I mean, I've got a lot of no argument parameters here. Get foo, right?
So you wouldn't use when you refer to it. You wouldn't use get this. You would just use the name.
Yeah, well, I mean, if you wanted to call like a getter. Okay, so since you're already in the class, there's no reason to call the getter directly. But if you wanted to, instead of last name, you could say get last name. Last name, if I can type it. There we go. You could do that. You could leave off the this because it's implicit, but it's best practice to always keep the this. Right? And whether or not it's best practice to call the getter or to just simply get this, half a dozen of one, 6 of another. Right? So roll it all the way back. There we go. Good questions. All right, so why am I still losing bytes over here? I'm losing them over here in the demo, right? I've got Jane, which takes a certain amount of memory. Jane's first name and last name, which also take a certain amount of memory. So let's go ahead and, once I'm done printing Jane, let's go ahead and free her up. Works perfectly. Let's ask Valgrind over here. Am I leaking anything anymore? Yes, you are. Not as much as before, but still you're definitely losing 9 bytes. Why? 1, 2, 3, 4, 5, 6, 7. Null terminator, null terminator. I count how many? 9. So what should I have done first? Freed her first name, freed her last name, then free her up. What if she had a bunch of things? Right? Probably want to put that into a function. And I'll leave that as an exercise for you. You'd want to free the first. What order would you want to do that in the, by the way? Free Jane and then her first name, then her last name? First name, last name, then Jane. Remember that these are boxes. This student is composed of things inside that box. If you delete the box, you can't get inside the box in order to free the things that are in there. All right, cool. So, to do, as any good programmer would that doesn't want to do something right now, what would you do? To do, write a proper free function. Yeah.
So if you delete the point, the chain, the big one, the first name and last name is permanent odds, so we can get to it.
Yep. Jane, first name, not print, but free. Jane, first name. And that only leaves Doe, which is going to be 1, 2, 3, 4 bytes that are going to be lost now. Let's go ahead and see. Valgrind says 4 bytes lost now. All right.
Would freeing Jane set the Jane to be null?
No, it would not. You still have that memory address. So here, I'll printf Jane's memory address, %p for a pointer, and Jane. There you go. The memory address is still valid, but if I attempted to access that memory address and say print Jane again, it may or may not be a segmentation fault. I'm 90% sure, 85% sure that it will be a segmentation fault. No, darn it. All right. I'm definitely not betting on Purdue for Purdue this weekend either. Then my luck is not with me. All right. So, but of course you can see that her first name has been freed, and so it's gone. The NUID, of course, certainly has been corrupted. If you really wanted to, of course, you could explicitly say Jane is now equal to null, but there's no point. All right. Good questions. All right, then let's see. Convenience methods for Java. I'll make sure you have that in the notes. I think the last thing that I would deal with is arrays of structures, maybe. Yeah, so let's talk about an array of structures here. And to do that, I'm going to need a couple more students here. So Jane, John, and Jam. I don't know. Jam, there we go. Just so that they all line up. Jane, John Doe, and Jam Smith. I'll just make them all freshmen. I will give them different numbers here, though. There we go. Oh, I don't know. 9, 8, 7, 6. There we go. All right. So I want to print all these students out. I'm going to go ahead and leave that commented. Print student, print student, print student. John, Jam. There we go. And run it. Yay, I've got 3 students now. And 3 students makes a class roster, right? So I need to put these into, not keeping them separate, but I'll go ahead and put them into an array, right? Now let's think about this for a second before I print all these things out. Let me go ahead and come back over here, and let's say that I don't want to just print a student. I want to print students. or print, say, a roster, so it has a completely different name. And I'm still going to give you a pointer to a student, but that pointer is going to be coupled with the number of students that are actually in that class, implying that that's not just one student anymore. That's a what? That's an array of students. Right? And of course, write documentation to make that absolutely clear. What does that look like now over here in student.c? Print roster. For int I equals 0, I is less than n, I plus plus. Do I already have a way of printing out one student? Sure. Why wouldn't I reuse it? S sub I. Okay, and then return. So print roster. Let's find out if this actually compiles first of all. Nope. Why? Expect on line 34. Not 34. Let's go up here. There we go. There's the error that I want. Line 44. Right? Incompatible type of print student. This is a S is a what? A pointer to a student. Right? So S sub I is dereferencing it. That is now not a pointer to a student, just a regular old student. Print student requires the memory address of this thing. So how do I get the memory address of this thing? Ampersand. Right? And now the compiler is perfectly happy about this. Now, of course, there's warning that they're unused variables, but we'll use them here shortly. Okay? Excellent. This at least is fine now. Now let's go over here into demo. I need to go ahead and, print roster, and I'll pass it in a roster. Right? That means that I need to create that roster. So help me. How do I create an array of students? One way I can do it is by saying that I want an array of 3 students. Okay. And then I can say that the roster sub 0 is equal to Jane, the roster sub 1 is equal to John, and the roster of 2 is equal to Jam. There we go. Can't think of another J. Jane, John. Well, 4 letters though. Jam, whatever. Who cares, right? Let's see if this works now. These are all, of course, used variables now, right? There we go. Print roster. Uh-oh, too few arguments to print roster. Well, that's because I need to pass in 3. There we go. All right, it's not going to let me do that. Why? Same problem as before, but in reverse. What is Jane? Jane is a pointer to a student. What is R sub 0? That is a student. So how do I take a pointer to a student and turn it into a regular old student? Dereference. Dereference and dereference. There's still a problem with this though, but the compiler is going to be perfectly happy about this now. Right? I'm not printing anything else in this function. That print roster is taking care of everything for me. The problem here is, let's think about the memory situation. In fact, I'll put it up on the board here. I think everybody can see me on the webcam, hopefully. We've got Jane. Let's just take Jane here. Right? Jane is a pointer to this student object right here. Student. Right? Roster is an array of students. So here's that roster. 1, 2, 3 things. And this is a full student. Right? So I've actually got these 2 memory chunks here that represent students. On line 17, when I dereference it, what I do is I jump to this student and I copy everything over into this memory location right here. After which, what about this memory over here? I've duplicated everything. Right? Jane Doe 1, 2, 3, 4. Jane Doe 1, 2, 3, 4. I've dereferenced it just so that I can copy everything over. Right? I've got 2 copies. In the main, this is not that bad. Right? But ultimately, if I did this in like a function or something like that, then the original memory that I allocated up here would be lost. It would be leaked out. And also duplication. Why are you doing this twice? Okay? So you could do something like this. All right? And in fact, you could fix this even further and say student star roster is equal to student star malloc. Right? Now it's not, at least it's not statically declared. Malloc size of student. How many of them do you want? 3 of them, so I can fit them all in there. Right? This is only slightly better. This situation that I drew up here is still the same. It's just that now instead of this thing being static, now it's dynamically allocated using malloc. Right? So what's an alternative? An alternative, and we'll go over this again on Tuesday with a full diagram that's not up on the whiteboard. But here's an alternative. Here's my roster. I'll make it into 4. What if each one of these didn't contain a student, but instead contained a student pointer? And then there's this object over here that is an actual student. And then there's this pointer over here that points to this one. There's this pointer that points to a different one, etc. Right? Now, what does this thing look like? It's an array of pointers. We've seen that before, right? 2D arrays. 2D arrays where this is pointing to an array of students. Well, that array is just of size 1, right? Instead of having, 50 integers hanging off the end of this, forget about it. Just one student, just one integer. And what would that look like now? Alternative. Student star star R. Let me go ahead and get rid of all this. Let's go ahead and get it to a working spot, and then we'll review it on Tuesday with proper diagrams. Student star star. There we go. And a call to malloc. How many of them do you want? I wanted 3, right? Let me just put that into a variable so I don't have to keep resetting it. All right. Size of times n. But what do you want? Do you want just students? You want a student pointer. Once you've done that, r sub 0 is equal now to Jane. Why did I do it like that instead of dereferencing it? Yeah, it already exists. I'm just making the pointer point to it. Right? And r sub 1 is equal to John. R sub 2 is equal to Jam. Right? Now, no memory leaks whatsoever, and I just have a bunch of pointers pointing to all of these things hanging out in the ether. Right? There's a third one that we'll go on, a third way of doing this that we'll go over on Tuesday as well, because we have plenty of time. But otherwise, let's go ahead and see if it compiles. No, but that's just because print roster doesn't take an array of students anymore. It takes an array of students, not an array of student pointers. That's all right. We can go ahead and fix that. Ignore that magic for now. It makes it easier. Right? And we'll change this print roster into taking an array of pointers to students. Now, how does that change the dynamic here? Each s sub I, or r sub I, is already a pointer. I don't need to reference it to give you the memory address because it is a memory address. Yay, we're all back to 1. There will be memory leaks here because I'm not cleaning up in the main, but of course you can ignore those. So there's yet another way of doing this. And again, there's a third way of doing this. Visually here, I won't show you the whole thing. We'll review it on Monday, but these could be all over the place. Right? This one could be located in one part of memory. This one could be located completely somewhere else. Right? What I want to do is I wanted to have the best of both worlds. I don't want these things just all over memory, right, in a fragmented way. What I'm going to do is I'm going to make a second array here that is all of my students, my roster, all contiguously allocated. They're all together. And then I'll do everything through pointers. So that I'll point this one to this one, point this one to this one, point to this one, oh, to that one, sorry. Right? Dot, dot, dot. This gives me the best of both worlds. All my pointers are contiguously allocated. All of my structures are contiguously allocated. But I can do everything through pointers. I can pass a pointer. I can return a pointer. I only have to deal with everything with pointers. And not only that, but what if I wanted to swap these two things? I'm going to sort the roster based on GPA, highest GPA to lowest GPA. Right? Do I have to take this guy, Jane up here, or say Jane's down here, and I'm up here, but we're out of order because she has a higher GPA? Do I have to change those? Nope. All I have to do is change pointers. And everything is super, super efficient. But you have to think completely 100% in terms of pointers and memory locations. Yeah?
So you want the students to be in a group?
Yeah, all contiguously allocated.
So it's easier to operate with them?
Yeah, because otherwise, I mean, that one could be located in one page, that one could be located in a different page in memory, and you could be swapping memory in and out or whatever. This solution gives you the best of both worlds. Now, nothing that you're going to do in this class is going to require the precision and fine control like this. So if you wanted to just do it the quick and dirty way like this, that's fine. Right? But this is also proper. All right, questions? Okay, well then we'll review that on Tuesday then. All right, have a good weekend.